2, 1. So welcome to the video. I want to show how we can come up with the derivatives of sine, cos, and tangent. So what are those derivatives? Now in calculus, once you kind of get started, you will cover typically polynomials, you'll do some rationals, you're going to do all kinds of different rules with respect to derivatives. So you have the chain rule, you have derivative for composite functions, and you have all kinds of these combinations that you can utilize. But once you settle on those polynomials and those rationals, you will slowly get shifted towards kind of trigonometric functions. So here are the main three, and I want to show you how these derivatives actually come about. So I'm not going to be applying these derivatives. I'm just going to show you first in this video how you can actually think about obtaining the derivative, all right, kind of from scratch. Now, in order to do that, we are going to be relying on the compound angle formulas. So my assumption is that you've done some trigonometry. Now, if you forgot about the compound angle formulas and you want to know where these formulas come from, so this is kind of trigonometric identities, I'm going to put up a link up above for anyone who's really interested. Now, you don't need to watch that video, but if you want to know where these compound angles are coming from, I do show it in that video. So I'm going to just use it here to help us along. So let's take the first one. So my first derivative that I'm interested in, and once I have this one, all the other ones will actually fall apart for us. So they're going to be so much easier to be able to work with. So here is the derivative of sine x. Now it says that the answer is cosx. So that's not very complicated to try to memorize, and most of you will do that. But how would you actually show this? Well, you would have to kind of go back to the first principles of defining a derivative from limits, and that kind of first principles tells us that we have the limit as h is approaching to 0 of our function. Now our function in this case is nothing else but simply sine x, so that is our function that we're trying to find the derivative of. So that would mean that we're going to be substituting. That's going to be sine of x plus h minus sine of just x, and that's going to be all over h. And now in order to find that this is cos x, we're going to have to do a little bit of massaging. All right, so let's take a look. First of all, what I'm going to do is I'm going to use the compound angle formula for this right here. So notice, if I have sine of one angle plus another angle, then I can use this entire compound angle formula to be able to find that out. So what that says is that this entire thing, I'm going to just kind of shift it over here. So limit as h is approaching to 0 of this, which is nothing else but simply sine of x multiplied by cos of h, plus this is going to be now sine of h multiplied by cos of x. So that's the entire thing, and that is coming from right here. So notice sine, cos, plus cos, and sine. So that's what I have right there. Now, all of this, I still can't forget that I have a minus sine of x right here that I'm going to have at the end. And all of this is all over h. Now, if I massage this a little bit, so what I'm going to do is I'm going to take this right here and this right here, because both of them have sine x. I'm going to factor that sine x out. So that's going to give me is sine x, and then factored out, I'm going to have cos h minus 1. And now I'm going to bring this h, which is in the denominator. Okay, so I'm going to just bring it over here. So that's what I have. So I've done this minus this, took out my sine x, and I still have that h over that. Now I still have plus notice I'm going to take this cos x in front. I'm going to just swap it with the sine h, and I'm going to put that h over here. So now I should, or you should, see that the above line is exactly the same here. I've just kind of reordered this. Now, of course, this is still as the limit is approaching. So h is approaching to 0. So that's still in here. And now what I want to be able to do, notice that this doesn't have an h and this doesn't have an h. So I've really just grouped this right here together. And I'm going to duplicate this. Okay, I'm going to put it on the side here. And with the other term, I have this term. I'm going to duplicate it and put it over here. Now, if I'm going to apply the limit as h is approaching to 0, now I have to apply it, so by the limit properties, both to here, and I have to apply it to here. And I want to now find out what these two are equal to. So what is this equal to, the way that it is put together, and what is this equal to? Now, algebraically, if we wanted to be able to show this, I'm going to kind of provide to you and show you that this entire thing actually is nothing else but 0. And this entire thing is nothing else but 1. So if I'm capable of showing you that, then you will notice that, oh, okay, so this entire thing just goes to 0. And 0 times sine x is 0. And if this entire thing right here will go to 1, then 1 times cos x will mean that the entire thing, so this, is going to be nothing else but cos x, which indeed is the derivative that we want to be able to show here. That's what we are claiming. So I have to be, or I have to have the skill, okay, or the kind of aptitude to be able to show these two limits. These two limits are not very easy to show. And most of the time, so students kind of going into grade 12, seeing this for the first time, they're not going to have the actual skills in terms of proving to be able to show that the left one, so this one right here, that you see here, is equal to 0, that limit, and the right one, which is this one, is equal to 1. To show that would actually take quite a lot of work. So I'm going to cheat a little bit, and I want to show you visually that this indeed is the case, that these limits are 0 and 1 respectively. So what I have done is I have taken these two, so I have taken sine of h over h as h is approaching to 0, and I'm going to plot it on decimals, and I have taken this and I have plotted it on decimals, so basically like a function. And then I want to let h go to 0 slowly, and I want to see what happens here. So if I'm going to do that, now I'm going to just take out decimals for these two instances. Now I've prepared, okay, this, and what I will do is I will add it, okay, in the kind of show notes in the video, so you can look down, okay, pop up the actual information, the description for the video, and I'll link this decimals graph so you can plot it out yourself and then play around with it. So here's the first one. So sine of h divided by h. So that's the first one. So if I take this, okay, I'm going to open this up. So notice I plotted it as a function of h. And now what I'm doing is, if you plot this, you will notice that, hey, this graph for all h, so it doesn't matter if it's negative or positive, and again, because we want the limit, so we want it to come and kind of go towards exactly the same point from the right-hand side and from the left-hand side. So as h tends towards 0. So imagine that your x-axis is your h, and now I'm going to be bringing back and then seeing what happens. So I can see that this graph at 0, it looks like it's at 1. But if you go to 1, it should be undefined because we have an h in there, and indeed, that's what you see there on the screen. It's undefined. But limits, okay, the way that they work is h approaches 0. It's never 0. It just gets smaller and smaller and smaller. So we want to see what is happening to the left and to the right of it. So now what I'm going to do is, if you take a look on the left-hand side of decimals, where I have put in f at a and then f at minus a, so I am approaching, okay, from the left and the right, and you will see that this is nothing else, as I play this throughout, notice that the 2 points, that is where your h is. So your h is getting smaller and smaller and smaller, and it is just tracing this actual graph of sine of h divided by h. And now notice that they're going to tend to what? It tends to 1. So it just goes straight up to 1. It's undefined there, but both from the left and the right, this indeed tends towards 1. So if I go back here, so that is exactly what I wanted to be able to see. This limit is just 1. And you saw that visually, that it's happening. It's not defined at 0, because we have an undefined function there at 0. However, that limit exists, and it's equal to 1. Now, what about cos of h minus 1 over h? So let's see if that indeed also equals to 0. So now I'm going to collapse this, okay, and remove it. And now, as you can see there, what I have, I'm going to bring back, okay, my h and move it way further out. Now I called it a here because I'm substituting it in. Here is the folder of that cos h minus 1 all over h. Now I'm going to plot this whole thing. Notice it looks different, but what do you notice? That this function, as h tends towards 0, also is going and tending towards 0 as well. So if I now play this, so notice that is bringing h and it's getting closer and closer to 0. So those are values of h, and I'm just reducing it. So now it's 5, now it's getting to 4, okay, and now you're going to see that it very quickly starts jumping over, and it gets to what? You can see there, bam, okay? It just happened to be at 0. So there you have it, okay? And you can just kind of play this back and forth. Again, I'll point that link and share this decimals so you can have it to play around with. Now, that is showing me that that cos h minus 1 over h, that limit is actually 0. And if that is indeed true, now I've shown this visually, not algebraically to you, so that is much different. However, it does the trick for us to be able to hopefully show you that indeed, based from first principles and using the compound angle formula, so splitting up the sine x plus h into 2 forms, changing it back, moving around the h, okay, and taking the limit of those 2, we notice that the result indeed is equal to exactly what we wanted, that the derivative of sine x is equal to just cos x. And that is what we see right there. Now, what about the other ones? So now that we have this, we can actually cheat a little bit. So we don't have to do the same grueling aspect. So within here, if I want to know the derivative of cos x, well, the first thing that I'm going to actually do, now cos x, you may remember from your actual trig identities, this is nothing else but simply sine of x plus pi over 2. Now this pi over 2, so that's in radians, so that is 90 degrees. So these two are equivalent. So that is a trig identity that we're using. Now, why am I using that? Because if these two are equal, then instead of taking the derivative of this, I've just shown you what the actual derivative is of sine And within here, so if I take this and take the derivative of that, I can do that without actually even using first principles. I can just refer back to what I just did. So if I want to take the derivative of this entire thing with respect to x, well, then this is nothing else but the derivative of this. And I'm going to just use composite functions. So this is the derivative. So now the derivative of sine is simply cos of whatever you have inside of your argument multiplied by, okay, whatever the derivative of x plus pi over 2 is, right? But that is not very difficult. Well, this is a constant. The derivative of x is just 1, so really this is just nothing else but multiplying by 1. So my derivative right here is this, of that. Now, that still doesn't look like what I want it to look like, of course. Okay, and within here, again, so from here, using the compound angle, so this right here, so compound angle formulas, you will notice that if I take a look and use this, let me copy this, bring it down, I'm just going to show you. So this is what we have, where your angle 1, that's your x, angle 2, that's your pi over 2, or just 90 degrees. So that means that if I look at this, I can say that this is nothing else but simply cos of x times cos of pi over 2, so that's this term, minus sine of the first angle, which is x, times sine of the second one, which is pi over 2. And wait a minute, cos of pi over 2, well, what is that? Well, that's just 0, right? That's 90 degrees. Cos of 90 is 0. So this entire term falls off. This is just 0. And sine of pi over 2, or sine of 90 degrees, well, that's just 1. So what do I have left here? I have just negative sine x. And that is exactly what we were looking for. We were trying to find the derivative of cos x. So what I did was I just simply said cos x is equal to sine x plus 90 degrees, or pi over 2 in radians. Now you take the derivative of that, which is something that we know, the derivative of sine right here. It's just cos of x. So I have done that here. And then I've used the compound formula to show you and break down that indeed that is the derivative. All right, so that's 2 of them. Now, what about the last one? So the last one that we have is your 10x derivative. So let me copy this. Let's bring it down and let's actually use everything that we know from calculus here. So how are we going to show this? Well, do I have to go back to first principles? No, not really. Once you know the derivative of sine and you know the derivative of cos, then you can find the derivative of 10. Now, please remember that 10x is nothing else but simply sine x all over cos x. That's just by definition what 10x is. So if you want to take the derivative of this, well, that's not a problem. This is simply by the quotient rule. So if we take the derivative of this by the quotient rule, then we have, what's the derivative of sine x? Well, we know, we just showed it, it was cos x. That's going to be multiplied by your denominator, so that's also multiplied by cos x, minus, I'm using the quotient rule. Now that's going to be now sine x multiplied by the derivative of the denominator. So the derivative of the denominator is negative sine x. And that whole thing is divided by, wait a minute, this is just cos x squared. That's what this is, which we typically just simply write cos squared x like this. So those two mean the same thing. And now from here, the numerator, so all of this that you see here, if I'm going to write that out, that's going to be cos squared x. Negative and negative is a positive. Sin x times sin x is just sin squared x all over cos squared x. But what is this equal to? Right here. Cos squared plus sin squared is always equal to 1. If you forgot about that, okay, from way back, put up a link up above there for you. So within here, so this is just 1 over cos squared x. But what is 1 over cos squared x? That's the definition of secant squared x. So there you have your 3 derivatives for sine, cos, and tangent. All right, thanks for watching. We'll hopefully see you in a future video. Happy studying and welcome to calculus. Bye, everybody.